The sun runs on fusion. And since 1950, we have been trying to replicate that same process here on Earth. The reason we've kept trying is that just 1 gram of fusion fuel releases as much energy as 11 tons of coal. This extraordinary fuel is deuterium fused with tritium, which produces helium and releases 17.6 MeV of energy. But there's a problem. Nuclei violently repel each other. To fuse, they must quantum tunnel through that Coulomb barrier. Overcoming that barrier requires 3 things happening simultaneously: extreme temperature, high density, and long confinement time. The machine designed to deliver all 3 is the tokamak, a torus-shaped reactor that confines plasma with helical magnetic fields. The largest tokamak ever built, ITER, uses superconducting coils carrying 68,000 amps at 4 Kelvin to create those fields. Once the fields are established, 3 massive heating systems blast the plasma to 150 million degrees Celsius. That's 10 times hotter than the core of the sun necessary, because we don't have the sun's immense gravity to help. At those temperatures, matter enters its 4th state, plasma, a soup of fully ionized free electrons and nuclei. But plasma this extreme is violently unstable. Millisecond feedback control systems are needed to prevent catastrophic disruptions. Even if we stabilize it, the exhaust heat must be handled by a diverter that can withstand 20 megawatts per square meter continuously. Meanwhile, the reactor wall faces another job: a breeding blanket that absorbs fusion neutrons and breeds its own tritium fuel. That's essential, because plasma damages everything it touches permanently, so the blanket must be self-healing. The grand experiment to prove all this is ITER, designed to produce 500 megawatts of fusion power from 50 megawatts, input a Q factor of 10. That would sustain 150 million degrees hotter than any place in the solar system for minutes at a time. A completely different design, the Stellarator, uses impossibly complex coils to confine plasma without any internal current, aiming for steady state. The promise of these machines was validated in December 2022 when the National Ignition Facility achieved Q above 1 the first time ever. In fact, Q has grown exponentially for 60 years, finally passing 1 in 2022, proving fusion is physically achievable. One obstacle still robs us of performance. Plasma turbulence carries heat outward from the core, cutting confinement time dramatically. We counter it with H mode, where plasma edge flows spontaneously suppress that turbulence, doubling confinement time. Today, AI control systems can spot and respond to plasma instabilities in a millisecond, far faster than any human operator. But there's a fuel bottleneck. The entire global tritium supply is just 25 kilograms, while a single power plant would consume 55 kilograms per year. The breeding blanket solves this by generating more tritium than it consumes, achieving a self-fueling ratio of 1.05. Magnet innovation is also accelerating progress. Spark's IBCO superconducting magnets reach 20 Tesla, enabling a machine 35 times smaller than ITER to achieve the same Q. This has attracted $6 billion in private investment across over 30 fusion companies, all racing toward commercial fusion electricity. Among them, Helion's unique approach collides plasma vortices and converts the fusion energy directly to electricity, bypassing steam turbines entirely. However, the neutrons released by fusion carry 7 times the energy of fission neutrons, causing 7 times more material damage per impact. To survive, new materials like odds, steel, and silicon carbide composites are being engineered to withstand neutron doses that would destroy conventional metals. The broader technology revolution, quantum computing, superconductors, carbon nanotubes, is converging to enable fusion's progress. Importantly, fusion doesn't need to beat solar on cost, it just needs to work where solar cannot, providing baseload power everywhere. We monitor the invisible inferno with lasers, microwaves, and optical emission, measuring everything inside the plasma without touching it. All maintenance must be done by robots, since neutron activation makes direct human access to the reactor core impossible. The full energy chain from fusion plasma to electricity is: neutrons heat the blanket, that heat makes steam, and the steam drives a turbine. The physics is now clear and solved. The remaining engineering challenges place commercial fusion electricity 15 to 30 years away. When it arrives, fusion will deliver energy abundance from seawater and lithium, accessible to every nation on Earth. So I ask you, what year do you think fusion electricity will arrive? Share your prediction in the comments. Picture it, inside the plasma, at 150 million degrees, 500 megawatts of fusion energy, burning like a miniature star. Fusion doesn't just meet energy demand, it removes the supply constraint entirely. Energy becomes unlimited. They've said fusion is 30 years away for the last 70 years, but that's because it's been progressing exponentially the whole time. Think of the three fires: chemical fire, then fission fire, now fusion fire. Each is 1,000,000 times more powerful than the last. One has burned for 4.6 billion years, the other has burned for only seconds. Both are stars, and we're building one on Earth. Private milestones are now set. Spark aims for net gain by 2028, Helion the same year, with commercial fusion targeted before 2050. If this changed how you see energy's future, subscribe to NexaVision, new videos every Wednesday. If the sun looks different to you now, hit the like button. Thank you for going inside a fusion reactor. The star on Earth is almost lit.